Hello, everybody. Today, Mr. Kaoru Ono will give the continuation of his talk last week on the Lagrangian Floer theory on orbifolds, and he should give us explain more about the application of Lagrangian Floer homology theory.
Okay. Thank you very much. And last time I spent too much time on user story, and then I didn't come to this orbifold story. So maybe I start from orbifold story today. So for me, it's rather convenient to consider orbifold as a proper data group, right? So it consists of several things, like X0 is a smooth manifold, X1 is also a smooth manifold, and X0 is the space of objects, and X1 is the space of morphisms. And then we have structure maps like S and T and M, the convolution things, and then a unit, and also this inverse. So I don't really write down all the properties today, but maybe I may just abbreviate this thing by this. Although we have also MUI and with some properties, but somehow today I just write it in this way. Okay. And then I consider the following thing. So let's consider the functor. So Y is also another proprietary groupoid, and then this is the functor, maybe F, so that F0 is a morphism on object level, map on the object level, F1 is a map on this morphism level, and then we
Like to speak now?
Yes.
We have
Yes.
a signal.
Yes.
More test.
Test.
Yes, now we have a good signal.
Okay. So they are supposed to be C-infinity stuff. And so such a things actually we may call strict morphisms. From X to Y. But we also need so-called refinement. So today refinement means the following. So X0 is a space of object. Let's suppose that maybe it has open covering like this. And then I consider U0 is just a disjoint union of this U lambda. And then we can hook up this U1 as follows. So here I have X1, and then here I have maybe S and T, and then going to X0 times X0, and then here I have U0 times U0, and then U1 is defined as a pullback of this. And then again, this U1, U0 is a groupoid. I forgot, I just abbreviate all the properties. Maybe I did not by U. And we call such a U as a refinement of X. So it's a refinement of X. But in fact, it is, okay, so maybe I have to remember another thing. So I have a space of object, and then I want to have a map like this. So what is this? So this is actually the coordinate space of x0 by x. Namely, if we have two objects, and then these two are equivalent if and only if there is some morphism x1, so that S of A is equal to x and T of A is equal to x prime. So I may denote this projection by pi. Okay.
The arrows go, these arrows on this.
This one.
Oh, the previous one, on the previous green or the one which is behind.
Behind.
They go in the opposite direction, right? These two arrows on the right hand side, S and T. So they go from x0 to x1 to x0, right?
Ah, sorry. Sorry. Very sorry. Very sorry for this. And okay. So then maybe we can also consider the case that so we consider family of open subset. So maybe let the lambda a family of open. Sorry. This is everything actually open. And if I consider the union of pi of u lambda is equal to this x, then we can also do the similar things. So also take this u0 as a disjoint union of u lambda, and then you can do the same thing. And it covers whole part of this cos space. So therefore, yeah, we can also work with it. But anyway, so refinement is this sense, in this sense or this sense. So then the morphism from x to y is just x to y. No, sorry. Just u to y, and then this x. So this is a refinement, and this is strict morphism. And in fact, this is a groupoid. So this one consists of these things. This is strict, and this is refinement. And then, so then the morphism between morphisms are just the following. So I have x, maybe I have u, and then y here, this strict and this refinement, and then maybe u prime this refinement and strict. And then if there is some w, which is also refinement, and then these two may not really commute, but there is natural transformation between them. And in fact, you can choose a finer w and so on. So therefore, you may, in fact, we have to really modify this. But anyway, so roughly the morphism like u to x and u to y and u prime to x and u prime y, actually this diagram. So now I come to the symplectic case. So first I consider symplectic orbital. So again, so now in this X, but sorry, this X. So then in this case, I consider omega 0 and omega 1 as symplectic forms on this x0 and x1, and such that maybe S star of omega 0 is equal to omega 1 and T star of omega 0. So if it, so yeah, as I said, so the object over this groupoid is somehow object on the space of objects, so that space of morphism acts on it. But in this case, actually, these are differential forms, so therefore, one may put in this way. Maybe I have to put a bit more. And also, if we want to have an almost complex structure, so that is also a pair of J0 and J1. And then here I need to have S star of J1 is equal to J0 and S star, and T star of J1 is equal to J0 and T star. So then we call this kind of pair as a almost complex set over this symplectic obifold, and this is almost complex obifold. And when we consider symplectic obifold, then we may also consider this one with compatible with symplectic structure. Maybe I denote by omega is just a pair of these two with omega. That is somehow these are compatible with omega 0 and omega 1, right? So this is just a definition of symplectic obifold. So locally, for X, maybe just like a G and U. So G is a finite group, and U is a certain manifold, just maybe domain in the Euclidean space. And in this case, we have this omega is a symplectic form on this U, such that which is actually G invariant, which is so this is a symplectic local description of the symplectic obifold. Okay. So now I want to talk about holomorphic maps from obifold Riemann surface to the symplectic obifold. So like now I consider sigma, which is also a obifold or obifold Riemann surface, possibly with nodes. But this node may be obifold nodes. And so this one is also written as maybe sigma 1, sigma 0. And then I have this X. It is actually again X1, X0. And here I have J1 here and J0 here, where they are related in this way. And then first I consider the strict morphism, maybe F. So F is J1 holomorphic if and only if maybe F0 and F1 after J0 or J1 holomorphic map. So just such a thing. So sigma 0 going to X0, and here we have a Riemann surface structure. So it has a complex structure, and it also has a J0. So therefore, this one is holomorphic, and the other is with nodes.
No, so it's not going to be might be sigma this way.
Yes. So, but at worst nodes, so like this. like this. Yes. And what I said here is that this point may be a nodal point on both sides. So like here, this side may be this, and then maybe some group 0 by MZ. And then the other side is also D2, but the same type of stuff. But action maybe opposite if you coordinate this side and that side may be opposite. But so somehow, yes. Does it make sense? Yes. But anyway, so these things. And possibly we may also have nodal point here. So possibly we also have orbital point here. So here maybe also we have also some picture like this Z over N and Z or something. Yeah, such a thing may exist here. Like this. So we may have such orbital point, and also this node can be orbital things. And then but still you can talk about this. And refinement is actually just a refinement. So therefore, if you take the complex structure J0 and J1 here, then certainly you can put it back to this U0 space or U1 space. So therefore, that part is somehow okay. So just to restrict the complex structure to these things, refinement, and then in general, the holomorphic morphism is just such a strict holomorphic morphism from refinement of this guy to there. So this is the story. And so now I consider the following. So we can consider the moduli space, moduli of stable maps. So stable map is actually, as I defined before in the usual manifold case, is that automorphism group is finite. And here, again, we can talk about the automorphism of this guy, and then with actually compatible with this F. So that is the automorphism of this mapping. And we assume that the automorphism of this guy is finite, then we call it a stable map. And so in this case, maybe we have a maybe genus G underlying. I mean, if you forget about the orbifold structure, you have a usual Riemann surface, and then you have a genus. And then we have M1, Mk. So they are the order of this orbifold point at the node. And then, today I just take A. So A is just a homology class of this underlying map. Because if you have this one certainly induces a map between this thing. And so this underlying space of this guy is just forget this orbifold structure. And so therefore you can talk about this image of the fundamental class and this A. So if when I write this way, then Z equals to L. This so this guy. And this one is also groupoid because morphisms, the space of morphism actually groupoid. So therefore, although I write this way, actually it is again groupoid. And so then somehow you may also consider aberration map at this mark point, and then this one actually map to so-called inertia things. So certainly, yeah, I can maybe I can define this one bit more fine way, and then I can define it. But today maybe I just take this course space and then do this. So what does it mean? So maybe I have to come back to this IX.
The dimension, it's like depending on M's and the others.
The dimension of this thing. So basically, you know the usual story. Usual story. So okay. So usual story is the following. So if you have a U from this Riemann surface to this X, and then the dimension of the modular space, maybe with K mark point, right? And G and K and A is equal to 2 times dimension of N. Sorry. I have to say this, yes. So N times 1 minus G plus sorry. N is actually half dimension of X, yes. And then here I need a C1 A pair with C1X, so C1 TX and A. And then plus this K. And then I have to add 3G minus 1. So this is the dimension of the modular space, 3G minus 3. And then I have a K mark point. So therefore, this is dimension. And so this is just a total genus and then multiply with the rank. So this is a usual story. And here, in the OB4 case, so these are actually numbers, but the problem is this thing. So if you just consider, say, the Stern-Bayes theory, and then try to define this kind of stuff, maybe try to define this kind of stuff, then it may, so maybe underlying thing is actually stay in H2 of this X, then rationals. Yeah. And so therefore somehow, because this is an OB4 bundle, so there is a way to somehow regularize it, to regularize. So maybe I can tell you this later, maybe. But so if you have this vector bundle in the OB4 sense, a homomorphic vector bundle on the OB4 sense, then there is a way to regularize it, to make this one integral. So this is actually just rational things, and then there are some correction term coming from this regularization process, and so then after that, actually you can use the same formula. So this part is actually replaced by the first rank class regularized one. No. This is actually still no Lagrangian yet. Yes. Yeah, later I will introduce this. But you are talking about this perturbation technique is somehow.
I don't know. Maybe it's really like.
Yeah, actually the story is almost the same if you consider this kind of Lagrangian structure stuff. And then we need to cook up these obstruction bundles. And so we take sufficient many such a stable map so that their neighborhood cover the whole thing. But whole thing means that the whole core space for course space, I forgot to, so for this course space, so I take sufficient many stable maps, and then I take obstruction space over there. So then I can extend this obstruction bound to the neighborhood, and then try to cover the whole thing. And the thing is that, so in this case, you have always a symmetry. So we have to consider obstruction boundary or obstruction space is invariant under the automorphisms, and then extend it and so on. So only thing we need to care is that, yeah, when we take this such kind of obstruction boundary, we need to make it invariant under the automorphisms.
You know, like as usual, typically if you try to develop stuff, even in the simplest situation, like it's not you. The reparameterization maps, okay, so they are normally homomorphic curves of trajectories. They're typically not smooth in the normal sense. So
Yeah.
it's like here you also.
Yes. Yeah. So that's true. That's the same thing. And in fact, we have smoothness of this guy. After we really need to introduce some coordinate, which is not really coming from the complex coordinate on the modular space of the domain curve. We take another things. And so this is a little bit technical, but it is written in about one of the papers, so exponential decay and so on. So anyway, so this is, yes, we can also do this, but I want to say that there may be little different point from user case. So what is different from user case? Yes.
All points on the Riemann surface.
Yes.
Have to orbit 4 points on the corresponding symplectic manifolds.
Yes. So maybe I have to say, so yes. So maybe I have to say one point. It is very related to your questions. So there is actually one requirement, because I want to explain the necessity of this requirement. So locally, it is actually mapping from this disk going to this G, maybe U or something. So this is a pair, like a D2 going to this U, maybe this is 0 things. And then I also have another one is gamma going to G by phi. It is actually a group homomorphism. So if you just write it, and then this thing is exactly the same as these things, because at least in this case, gamma and G are finite or discrete. So therefore, yeah, F1 is somehow, if you consider the first component, they are actually locally constant. So therefore, it gives us a map like this. And so we have to assume that this one is injective. So this is, I always assume this. So if I have this sort of point, and then I should have a map to X0 from this, right? And here, this group gamma acts, and here X1 acts, but locally, maybe I can say that here is mapping to U, and then some group G acts here, and then there is a homomorphism like this. And then if I have a stabilizer here, and then it mapped to here, but this is actually injective homomorphism. So therefore, it's also stabilizer there. So this is one. And then after mentioning this, I come to the following things. So that is about something related to the compactness of the modular space. So one of the arguments which is necessary to show compactness. So when we consider a family of obifold Riemann surface with possibly nodal points to X, maybe I consider maybe UI, and then okay, then we just want to ask whether there is limit of this guy or not. And here I assume that all UI actually belong to this class. So therefore energy is actually bounded. Okay, so all this energy bounded. So is uniformly bounded. And then certainly you may do this bubbling of phenomena, or maybe sometimes if Riemann surface degenerate, then you have this kind of neck is actually appearing, and then neck is long and long and so on. So the point is somehow this thing. So if you have long neck, and then it may actually split into two parts. So maybe if I have something here and something here and then here. So this is one piece and this is another piece. Okay. In such a case, actually, we have some sort of exponential decay estimate. So therefore, here the derivative is getting exponentially getting smaller and smaller. So therefore, somehow if you go through this, then it doesn't really move so much. The length of the loop cannot go so far away. But so now I consider this x0 here, and I want to map this one to here, but it may not be possible because if you forget about this part, and this part is not simply connected. And so if you have a loop, and this loop may not be really closed up in the image. So I just cut it. So roughly, I just cut it here. So then cut it open. So like this, and then I have this kind of path. And then original one and this one, certainly if I cut it at this line, so therefore they are different spaces. But now I also introduce arrow, I mean the morphisms on this boundary cell. So I have these morphisms. Then I consider it a groupoid. So here in the interior, the morphism is just identity morphisms, only that one. But on the boundary, certainly we have identity morphisms, but also morphism from here to here. And here actually I have a morphism identity and from here to here. So somehow just to introduce some equivalence relation, you come back to this. And this equivalence relation certainly formulated in terms of groupoid. And so this is not proprietary groupoid. So therefore, if you like to make it proprietary groupoid, then maybe you can little bit sequence this and then glue them on the open part. So that's the way. But anyway, so you have here, And then now you can just map it to this x0 because this path is so short. And yes, if you know that, yes, so somehow the picture may be something like this. So you may have this, and you may have this, and lower boundary going to this, and upper boundary going to this. And then they are related by some group element G. So if you cut it open, then you have a map to this space. But then certainly it may not close up, but they are related by group element G because originally they are actually the equivalent point. So I have this. Then G is finite group. So therefore we can consider its order of group G. Maybe I just put it M. Then I just put the structure. I mean, so this is actually the punctured. So this part can be identified with punctured disk, and this part is also identified with punctured disk. And then I just, yes, so then somehow here I consider some group Z over MZ. Sorry. So then I consider something like this. So here to here, and this is actually quotient by Z over MZ. Like Z going to Z to the power M. And maybe here, maybe, yes. Similarly, you have this. So this is the reason why I say about this O before node. So because even though the whole Riemann surface sequence Riemann surfaces are all non-singular without any O before point, but if you take a limit and then there may be some nodes that have seen the O before node may appear. So this limit O before the structure can be seen from these mappings. So not only the sequence of domains, because sequence domain cannot really tell us what is the order of this. But because we have this mapping, so from here actually we can see this.
Structure, the group which is acting on the second disk, right hand side, has to be also Z over NZ.
Yes. But somehow they may act kind of oppositely.
Yeah, so one goes, one acts.
Yeah.
To be able to do it.
Yes. Because here actually maybe somehow dw equal to.
So going is basically if one coordinate is Z1, the other is Z2, so Z1 times Z2 is equal to
Something. Yes. Some sizes, yes. Yes. That's right. So then the first factor you may multiply the theta m, the m's root of unity, the primitive m's root of unity, and then the other side may be theta inverse. And so that kind of. Yes. Okay. So once I said this, so here I have this group element like eta generator, just to usual generator, smallest rotation by eta, and this eta is mapped to this G. So somehow in such a case, actually you can see how this one is defined. So you have an O before point, and then at this O before point, you have generator of this local group, and then look at the image of this group element by phi, and then you get some element in this sectors. Okay. So I think I define this Ix probably, but I may forget this. So because anyway, so I really need it later. So maybe I just remind what it is. So this is an answer. Cuboid, or maybe twist sector. So this one is also cuboid. So therefore I have this Ix 0. So this is maybe A, maybe 1, so that S of A is equal to T of A. And I of X1 is just A, the prime like this, and then maybe B here. Then B is also X1, and S of B is equal to A, and T of B is equal to A prime. And yes, oh, wait. They are related by A prime. A prime is related by B, A, B inverse or something. So this is this kind of stuff. So locally, in the case that G mu, in this case is I of G mu of 0 is just G and X, and this is G times U, so that G acts on X, then it's like this, and I of G U of 1 is equal to Gx going to G prime X prime by H, and then H sends X to X prime, and then G prime is equal to HG H inverse. And then you have these local descriptions. But anyway, so we have these relation maps, and therefore we may have these things. Okay. So let's take maybe alpha 1, alpha k, cohomology classes of this Ix. And then we may consider this alpha 1, alpha k, and G, and A. Here I have to write some M1 to MK, but okay, so this one is defined to be the integral of this MG A, then Bachelor class, and then everyone start alpha 1, and then maybe wedge, and UK star of alpha k. So for instance, in this case, maybe I consider alpha I, so ith thing, maybe this, sorry, maybe it's okay. So, and it's okay. Maybe I take this M, and also M. So here actually I consider all possible tuples M1 to MK, and then consider this. So this is actually all before the Gromov-Fichte invariant, and using 3-point function you can define all before quantum cohomology and so on. So this is actually Weyman chain runs all before the witnessing. So now I come to the Lagrangian Floer space. So first I have to consider the class of Lagrangians for which we develop Floer theory. And for this, somehow you may just recall all the result by Weinstein. So no, they use a good map and so on. Not the language is different, but yeah, just translated in this terminology. Okay. So what is Lagrangian now? So let's consider the usual case. If X omega is a manifold, symplectic manifold, and then L is a Lagrangian submanifold. So this is usually, as you know, so maybe I denote by I, then I star of omega is equal to 0, and the dimension is maximal possible dimension, so that half of this. So then this is Lagrangian manifold, but Weinstein, yeah, let's suppose that L is just a closed Lagrangian manifold, maybe for simplicity, and then what he says is that there is a neighborhood U of L, and also an anti-symplectic involution every tau, so that L is written as a exponent of tau. So this is not really Weinstein's theorem, but Weinstein says that the tubular neighborhood of Lagrangian submanifold can be identified with the tubular neighborhood of cotangent bundle of zero section. And then you have a fiber-wise multiplication by -1, and that is exactly gives you this. So therefore, this is no.
Equivalent to the
Equivalent, yeah. No, yeah, not equivalent. It follows from Weinstein. But anyway, so this. And then somehow we consider the following things. So we don't really need to consider global anti-symplectic involution, but at the beginning, I start from global ones. So, okay, so at the beginning, I just consider this. This is what we call symplectic lentifold. So let X, maybe this X1, X0, and omega 0, omega 1. So this is symplectic. Oh. No. This is very different. No. I define it. It is not really orientifold. This is a kind of analog what is called orientifold. So you consider this symplectic obifold, and then symplectic orientifold as over this is the following thing. So I take another proprietary groupoid, and then which is actually sitting in this kind of exact sequence. Maybe I take this epsilon, and maybe it may be better to put B here, like a clustering space, clustering stack. So this one is the following. So here I have x1 tilde, and here I have x1, and then this is actually inject to this x1 tilde, and then here I have epsilon, which goes to plus minus 1, and this is surjective. And here I have x0, and here I have x0, Then we have this kind of structure maps. This is the same thing. And then this is also this. Just a inverse image of +1 is nothing but x1. And then I have another one. So maybe I may denote it x1 is equal to epsilon inverse of x1. So this is okay. But maybe, yeah, sometime I may write it inverse image of -1. So this is not a groupoid. This is started with a groupoid. But this x1 tilde is a groupoid, but this one is not. But anyway, so you may consider such a thing. And then here, maybe I have this S tilde and T tilde, and here S and T. And then I assume that certainly this S tilde star of omega 0 is equal to T tilde star of omega 0 on this x1, certainly. But we consider S tilde star of omega 0 is equal to negative of T tilde star of omega 0 on this x minus 1. So in a sense, the element in x minus 1 is a germ of certain anti-symplectic diffeomorphism. Okay. Then
What about morphisms? I know about objects. I mean, x0 and x0 filled out the set.
yeah, this is the same. This is the same. This is the same. So locally, we have this g going to g tilde, and then this epsilon going to ±1. We have this kind of bigger sequence, and we have action of g on this u, but first of all, I have to assume that this action extends here. So we have to consider g tilde, this one. And so that, again, this g preserves omega, but element in this reverses omega. So this is local story. And I assume that this is still a finite group. Okay. Then I can say the following. Now I take maybe L, maybe L0. L0 is an element in this epsilon inverse of, maybe better to write it x minus 1, so that tau composed tau is equal to identity, or maybe just unit. And so then it in particular means that this S tau is equal to T tau. Otherwise, we cannot compose. So in particular, this one implies this. So now I can say that, so if I put this point, say x, then here I have u, then I have point x, then I have some germ of anti-symplectic diffeomorphism tau. So somehow I have a kind of germ of anti-symplectic diffeomorphism here. And then the fixed loci is somehow germ of Lagrangians. But now I consider this one. So actually, this one actually continued to this because this. Okay. Hmm? Hmm? So later, next next. Yes. Okay. And then L1 is the following. So I have this tau as here, maybe L0, and tau prime is also L0. And then I want to have this G. And then this G is an element in this X1, so that tau prime is equal to G tau G inverse. Yes. So I have to say that, yes. So I have G, so that this convolution makes sense. Namely, S of G must be S of tau is equal to T of tau, and T of G is equal to S of tau prime is equal to T of tau prime. Right? So this is now one example of Lagrangian what we consider. So we consider this like Kähler, and this Kähler is mapped to X. This Kähler is mapped to X. Namely, here I have L0 to this X0, because here I have tau, and then I send it to this S tau is the theta. And L1, so here, if L1 is this G, the tau G tau prime, right? Then this one is sent to just G in X1, right? So this one is actually mapped to this isomorphism. And now, so you can see that this also provides a legal point. So now the spin structure here. So spin structure on this L is just the spin structure on L0 with this L1 action. L1, yes, L1 action. So this is the same thing. So if we want to consider some object over this groupoid, and then this geometric object is object over the space object on which this space of morphism acts. So this is okay. Then I want to consider little bit more general situation. So a little bit more general situation means that this symplectic manifold need not be defined on the whole X, right? So therefore, we may consider following situation. Maybe I have some V, yes, some V inside of this X, and then consider this V0 with just the inverse image of this V inside of this X0 space. And then we can consider this symplectic groupoid related to this kind of things. And then we want to have some V tilde epsilon V plus minus 1 like this. So that this is actually symplectic orientifold. So somehow this one need not be defined the whole space, but so here I have some whole space, and then yeah, maybe we want to consider some sort of like shadow of Lagrangian inside of this, and then I just take some neighborhood weight, that is maybe this V, and then we have a map from here to here. So therefore, I take inverse limit V, which is inside of this V0, and then only consider symplectic orientifold over this thing. So that's enough. And then in this example, I only consider whole things, but it need not be this. So I consider this tau in this V minus 1 in this case, and this tau is equal to identity. And it may contain several connected components. So therefore, I take something like, I take some L, no, I take this L0, which is actually a union of connected components. Of these things, such that which is invariant under V1 action. So V1, sorry, this one maybe I also denoted by V. And then the space of morphism is actually denoted by V1. So this V1 acts on these things. And I consider the union of connected component of this, which is invariant at this V1, and that is this L0. So need not be the whole tau with this property, but maybe union of some component of this, which is invariant under X1 action. And then I can do the same thing, because I consider this one is invariant under this V1 action, so therefore this one does make sense. Okay, so this is a definition. Then I want to consider dihedral Richt effect, which we actually denote by I of X of A. So it's again a groupoid. Okay, so this one is the following. So it's like now it consists of pair tau1, tau2 in this L0 times L0, so that S of tau1 is equal to T of tau1 is equal to S of tau2 equal to T of tau2. So what was this? So I have a point, and then tau1 is a germ of anti-symplectic involutions. And so therefore I have also a germ of Lagrangian here. And it means that I have two of them. So a little more bigger picture. So maybe I have this, and then I have this involution, tau1, and I have another involution, tau2. And then this point is x. Then this is x. So this point is fixed by tau1, and this will be fixed tau2. So this is this thing. And then tau1, tau2 going to tau 1 prime, tau 2 prime, G. So this is the same thing. So again, this tau 1 prime is equal to G tau 1 G inverse, and tau 2 prime is equal to G tau 2 G inverse. Namely, I have another picture like this, tau 1 prime and tau 2 prime, and this is x prime, say. And then there is some arrow, some morphisms, which sends this picture to that picture. So this is one. And why I call it the heterotwisted sector? Okay, so this is the, yes, I need to really keep this, but maybe I need to this. So locally, what does it mean? So locally, it is actually here, tau 1, tau 2, and x. And tau 1, yes, tau 1, tau 2 element in epsilon inverse -1. And tau 1 square is equal to tau 2 square is equal to identity. And then tau 1 x equal to x, and tau 2 x is equal to x. So this is the local picture of this guy. But I have this g tilde here, and then g here, and then here plus minus 1, and this. So therefore, I can just here I have a tau 1, tau 2, both of them map to -1. So therefore, tau 2 can be written as g times tau 1 for some unique g, and g is in g. So if I write in this way, then this one can be identified with the following things. So tau 1 and g and x, so that tau 1 is inside of this epsilon inverse -1, and g is from g, and then tau 1 square is equal to identity, and g tau is equal to g inverse. So tau is the involution, therefore it is actually conjugation by tau, so this. And then tau 1 fixes x, and g fixes x. So they are actually in one-to-one correspondence. So instead of this tau 2, I just use this g to write it. Then here I can find this dihedral relations. So this is dihedral relations. So locally, actually, this one is actually this. So when I talk about this, in this case, actually, it corresponds to homomorphism from cyclic group to G. So in this case, actually, this is not like a cyclic group going to G. So this is the data here. But here, I have this pair of this pair of this actually gives me a homomorphism like this. So that time actually cyclic group, but here actually the dihedral group. Okay, then I need to say a bit more complicated things, but so here I consider the following things. So the following object is somehow not so difficult, but somehow takes some time to explain. So therefore, let me just omit this. So there is certain local system over this IXL. So this is O1 local system. And this is actually necessary. So this is the need for orientation issues. Of the moduli.
O1 means Z2, right?
Yes, sorry, Z2,
So-
yes.
so,
Plus minus 1 or? Yeah,
that's fine. Just assuring myself that.
yes.
Yeah.
Moduli of border stable maps. So I introduced something. So this is actually in the case of smooth simplex manifold and also pair of clean in the intersecting Lagrangian submanifold. This one was introduced in our book. And so we have this. No. This is actually our Lagrangian Floer theory. And so now I want to say similar thing here. So I consider similar picture, but now basically we consider the genus 0 case with connected boundary. So therefore, now we consider really literally this kind of picture. Maybe some point, maybe OB4 point, but like this. And also, yes. Okay. So there may be some sort of puncture here. But anyway, so this kind of stuff. And then again, we consider the limit, and then the limit actually come to this. And also this. Maybe I just come to the conclusion. Okay. And then, so if you look at this part, so now this is really a strip. So previously it's a cylinder, so therefore I need to cut. But now this is just a cylinder. And then I need to consider the mapping to, so like from here, mapping to this X0 space. And then this part may be mapped to some part like this. And this part may be mapped to another branch of Lagrangians. And then in the end, this thing and this thing may be mapped to this. So therefore, I don't know, this part may be mapped to this part. And the other part may be mapped to another part. So somehow in this case, if you look at this limit, you have a puncture. This puncture is actually mapped to this kind of sectors. So there are two branches of Lagrangians. So this one may be the fixed locus of tau 1, and this locus may be tau 2. So I just specified. So I have to, when you consider mapping from holomorphic mapping from here to here, then the Lagrangian boundary condition is actually just given by these two branches. So therefore, if I look at the limit, then I have this point with these two branches. So that is exactly this pair of involutions. And so therefore, this one lands at this space. So therefore, in this case, if I consider moduli space of border stable maps, and in this case, this evolution map lands at this IXL. And if I have an interior map point, which is also such a before points, and then maybe I have this F plus J runs in this IX. Then finally, the statement is that in this case, we have the following operations. So I have, say, M, K, beta. So in this case, actually, this is a mapping from, say, omega star of this I of X, L with this coefficient, tensor K, going to this omega star of this IX, L with this. The definition is exactly the same, but we need to have these two of these local systems in order to give some orientation, or maybe local orientation on the modular space. And we also have this Q, K, L, beta. This is somehow omega star of IX, tensor L, and then omega star of IX, L, theta, tensor K, going to this omega star of IX of L, theta. So this thing, if you sum them up, this one gives us filtered infinity structure, but now on this space. So this actually must give us. So this actually we have to really write the whole proof, but this one is somehow MK gives the filtered infinity structures on this omega star of I XL theta. So maybe I have no time to explain any kind of applications, but yeah, that's somehow all. Thank you very much.
Yes, first, you thought that you can explain everything stuff in one lecture, but now
Yes.
it's a bit more time because
Yes.
the background.
Somehow, yes.
Yes, listen, just even I wonder, when did you understood that run or before theory Cohomology is better to translate it in Lie groupoid language?
I don't know. So actually, if you are good at their way of I mean, organizing things, then I think there's no difference. But for me, actually, I don't really need to remember so many things because just X and sigma and X are groupoid. And then from there, actually, if you consider this refinement or maybe some strict morphisms, then we can get a notion of this.
Understood immediately, that's a better to write in Greek,
No, it actually it is maybe the same. So therefore, yeah, I don't know, that point may not be a point. Yeah, but so I think you can also do everything in Shenron's way to do this, like a dihedrated and so on. But for me, just a convenient way to put it. So that, yes, I don't really want to say that, yeah, there is a real advantage or something. Maybe, yes.
later. So that's at the moment there are not so much how to say symplectic stuff on the RB phone. I mean that's orange phone can be considered a generalization of manifold. So how much people already try to generalize that in that setting?
Actually, I don't really understand, but the question.
So I mean, Ron is the first person who tried to generalize a symplectic theory. those are deformed like that.
Yes, chain and run.
Yeah. And general, and then there are also many work on that duration of that gap.
You mean some computation or something?
And so that means that except the color theory, for example, there are a lot of kind of.
I think flow theory actually, not this way, but we can also do Hamilton flow theory in this manner somehow. And so the end result, if we just want to get some estimate number of fixed points or something, then that is actually maybe you may expect. But the formulation, how to formulate it, how you have this kind of twisted sector appearing in that. No, that is somehow. No. That is actually now we actually figure out with the Bofichen and do and binding one. So some part is written, but so Hamilton flow theory, and then once you have the Hamilton flow theory, certainly you can also talk about spectral invariant and so on. And
yes,
so that's so once you cook up the correct theory, and then those things actually almost straightforward.
And it's the same for contact.
Contact is not really by this, but possibly. Not, I don't really working on this on the contact case, but somehow, yes, I think so. Yeah, maybe you take a simplification or something, and then basically.
Is there some more question?
You need to take a diagonal.
Yes. Sorry. Yes. So yes. In fact, this that is the first case we actually studied. So thank you very much. Thank you very much. So okay, so you have this first manifold case, then you have this, and also you have this x times x, and then maybe minus omega plus omega stuff. And then here you have this kind of diagonal. And then here, maybe you have this quantum cohomology of x. And here you have theory of this diagonal, maybe kind of self-intersection stuff. And here we have this quantum product. And here we have some product which actually up to sign it is actually coming from this M2. And the question is whether they actually is isomorphic or not. And in fact it is. But when you consider this map, maybe omega is not good. Maybe I take some chain complex. And then I consider here, it again, we may start from some chain complex. And then over there, we have this infinity structure and so on. And certainly these two are the same thing. So therefore, if you just take kind of identity map from here to here, then is it really the map inducing this isomorphism? But it is not really the case. So in fact, so there is a map I, which is actually isomorphic, and then it induces isomorphism between these two modules. That's the first step. And secondly, we have these two algebras, and that is actually done by the Kenji and Yongen and Hiroshi in one of the papers, anti-symplectic involution or something. But now we also consider this kind of thing for Lagrangian flow theory. That somehow we really wanted to do. So here we also have this, instead of this, maybe I consider this kind of obifold. And here we also consider something like this, I of delta of something. And then we want to have this. So then I can at least tell you one thing. So here I consider this I of x. So this is a main character, main player in these things. And here I have something like this. And how can we understand these two things? So in fact, we have some morphism between this. To explain this, maybe I just do the similar thing as before. So here I may consider this kind of limit of the holomorphic cylinder here. And so then first I just open it up. And maybe here I take this, maybe this -1 and +1, and this is R directions. And then here is a 0. And then we just glue them together to get the cylinder. And here, so therefore I have here maybe U plus and U minus. So now I have this +1 and 0. And I take U plus as a second factor. And the first factor is maybe U minus composed with iota. So iota is actually complex conjugation. So iota is complex conjugation. And then, so this one is actually originally mapping to x, 0. And then this is actually mapping to x0 times x0 because I have these two factors. And so this thing, maybe I don't know, maybe this iota or something, maybe map to some group element acting here. So in this case, here the value of U plus U minus coincide. So therefore, the lower boundary is really mapped to the canonical diagonal. So here I take canonical. So how canonical or maybe x prime is equal to just x prime x. And then another one is actually these two are related by G. So therefore, for instance, if I take one point here, maybe P, and then U plus of P is equal to G of U minus of P, that is a relation. So therefore, this one is actually consistent of this diagonal, but this one consists of X and GX. And this one is actually a fixed point loci of tau. Maybe I just write to G. So maybe tau G is equal to, I forgot, maybe G inverse G and tau can or something like this. Maybe G inverse and G inverse, something like this. So this element it corresponds to already yes, sorry. The one. So I have this tau can and tau G, but also I can just consider pair tau can and this element. And this one certainly you can read off this G. So somehow, yeah, starting from this, actually you can have this G, and from this picture, you can have not only this diagonal tau can, but also we can read off this G in this way. So somehow you can also start from here, then any tau something can be written as in this form. Only this G inverse G tau can, that kind of forms. or maybe other things. Yes. So therefore, yes, you can just have a one-to-one correspondence with G and these things. And so therefore, we have somehow starting from this kind of point X with G, and then here I have Tau-Chan and this G inverse G. Tau-Chan. So this is a correspondent. And yes. So then somehow we can actually try to identify these two things. Yes. And to show this, actually, here we really need to use some operator pair. It's actually open close map. So using open close map and also some projections, actually, using such kind of construction, we cook up this. And so here actually we also have to cook up such a thing. So then the output is not this one, but output is this one. Then there's yes.
Okay, so can you speak a little bit?
Yes.